Hello, everyone. I'm Sujith Joseph. I work as a chief architect for enterprise search and AI in the data analytics organization in Cisco IT. I worked in enterprise search for over 19 years, starting from very K2 days, autonomy days, etc. What we do is we provide enterprise search services, search as a service offerings, generative AI services, enterprise AI services, including generative AI services, to broader teams all across Cisco. So let me talk about how we revolutionized. Can I go one slide, please? Back. When we talk about how we revolutionized search at Cisco with the help of AI, Elastic, and GCP. Now think about it for a moment, that you're searching for information online, and it takes ages for the results to load. Or if your company's support engineers are searching on millions of historical support tickets, and if the results returned were irrelevant, it would have certainly been a frustrating experience for them. It would have been a huge productivity loss as well. Well, these were some of the challenges that we faced with the legacy search, and we did reinvent search at Cisco with AI, Elastic, and GCP. Now, in this new platform, users of Cisco.com and our internet search users are being given direct answers to their queries or questions with links pointing them to paragraphs within these documents. The speed of the results were amazing. We saw up to 70% improvement in the global search response time, especially in the ABJC regions. Now, 90% of the Cisco's product support tickets are solved utilizing this new search platform, which we call it as reimage and topic search. This is a tool that our customers use to solve tickets. Now, what we saw is that there is a lot of feedback that we got, positive feedback when we rolled out, and here are some of them. So, well, what more can you expect from a search platform migration? We got the speed and the accuracy right. The results quality was better. They're able to find more relevant documents faster, which accelerated the case resolution time. In fact, they were able to save around 5,000 engineer hours per month, etc. We deployed this on the foundation of Elastic in GCP, deployed globally across these regions. Now, let me talk about the scale of the platform. We get around 1.07 billion queries a year, index around 195 million documents, and 1.23 billion records. We support around over 50 enterprise search applications across Cisco. Now, let me talk about the AI-powered search use cases. The first one is reimagine topic search. As I mentioned earlier, this is the tool that our support engineers use to search on historical support tickets, bugs, knowledge articles, bug attachments, etc. Pretty much everything that they need to solve a particular case. And one of the things that we've done is optimize it to make sure that the more recent documents and the clicked upon engaged documents are memory mapped, and the rest of the document goes in the warm nodes. So the memory map nodes are essentially the hot nodes. So there are around 52 million documents that are searchable here. We have around 20,000 users using it. We get around 12 million queries a year. Now I'll talk about some of the AI features that we rolled out in this topic search. One is key phrase extraction. That is, given the user query, we extract certain key phrases which are more similar to the entire query, especially when the query is long. We use that to augment the original query with some additional boost. So the way we use it is use something known as a keyword, which actually extracts 2 to 5 grams and figures out which of these n-grams are having a better cosine similarity against the embeddings of the entire query. The second aspect that we've rolled out is keyword ranking. So we use the bird attention weights of the keywords to figure out which queries needs to be ranked higher in the formation of the Elasticsearch query formation. And last, we use Bayesian optimization to use an ML-based approach to predict or generate the boost values for the Elasticsearch query. Given a large set of boost values per fields, we use AI to predict that values based on a golden data set so that we can avoid the trial and error on figuring out what are the exact values that you need to set for boost, etc. And now that we have figured out the search quality is good given a query, the question was, how do we generate the query given a support ticket? And we use generative AI to do that. And this is something that we did last year. So there are two models that we used. One was an ability to generate key phrases, just like I talked earlier, based on n-grams, and the semantic similarity between the n-grams to the entire support ticket embedding. So we used fine-tuned BERT embeddings for this. We've seen it rather than using a pre-trained model, fine-tuning the embedding model on our internal content gives you an edge in coefficient similarity. The second thing that we did is use T5 to train the model on a bunch of support tickets and the corresponding search queries. And given a new ticket, it can surprisingly generate good SEO queries to predict the search queries. And what we did is we picked up all of these queries and then sent it to Elastic and got the results. We cached in Firestore so that during inferencing time, we just pick it up from Firestore and serve it. We have started with T5, and then we moved to long T5. Now we are working on Llama 2 for over here. Now, we use, for the long T5 one, we use the Hugging Face TGA text generation inference for serving it in a Kubernetes deployment, GKE, in GKE, so that it can auto-scale, etc. So here is what the fine-tuning was all about. So essentially, the input data for the fine-tuning was the support ticket data, metadata, including the product symptom, the custom symptom, the title, etc., and some of the nodes. And then the output is a bunch of SEO queries separated by a separator. Now, the next, I'll talk about some of the AI innovations we rolled out in Cisco.com search and internet search. There are three things. One, we had an AI-powered Q&A search. Two, we used generative AI to generate questions from the passages in Cisco.com and use these questions as auto-suggestions in the UI. Third, auto-suggestion itself, some of the auto-suggestion itself are powered using an embeddings-based search. So let me talk a bit about the NQG, the neural question generation. So this was implemented in early 2020. So what we did is, during crawling and the document processing time, we used to extract the chunks from the paragraphs, from the documents, and index these chunks separately into Elastic. And during this extraction process, this is sent to multiple set of AI microservices running in GKE, which would then use, back in the day, we started with the UniLM model from Microsoft, and then we later on switched to T5 model. So this model would extract these questions, and these questions would get passed through a data cleansing process. Like for around 400,000 documents, it generated 80 million questions, and after data cleansing, it came down to around 8 million. So back in the day, this was done in 2020. So it was hallucinating a lot based on the models that we used, and we had to put a lot of rules and patterns matching to figure out what are the good ones to put out there. Now, the good thing is, because we knew the questions were generated from these chunks, and these were appearing as auto-suggestions, when the user clicks on it, we're able to direct the user to the right chunk which it was created upon. So, and if the user puts in a similar question, not exactly the same, we are able to find the best chunk for it based on the similarity between, there is a question-to-question similarity, there is a question-to-passage similarity over there, and bring the right passages, which is what I'll talk about next. And now we are looking at the newer, obviously, LLMs to figure out, can I do a better job than T5 using some of the larger models right now. And what is interesting is even what we figured out is if we use, say, something like GPT-4, we are able to, some of these questions are pretty long, probably like 15, 20 words. You can use an LLM to then summarize it back to 10 words to kind of normalize the size so that it looks good in the auto-suggestion. And it does a very good job in kind of normalizing it. without losing the meaning. So the next use case is the Q&A search. You have a user query. We're able to bring the right chunks to the end user, and this was done last year. So here, what we're doing is a hybrid search. So we get the results from semantic search results. We get the results from the BM25, and we get some information regarding the user behavior data, the click-through data, and bring it all together, and we're performing a hybrid search and doing an AI-based re-ranking based on these results to figure out what are the best passages to be displayed to the end user. And the last part is similar question recommendations. Once the user has seen a question in the passages, we are now then showing very similar questions based on the user interaction, and that happens based on question-to-question similarity. Now, let me talk a bit about the embeddings for this. So we initially started off with the pre-trained embeddings, and what we realized is when you fine-tune an embedding for a custom domain, the matching accuracy is great. For example, we have fine-tuned E5 models as well as MPNet models, especially for the Cisco.com corpus. And in our rating, it has performed well than ADA or BGE or E5 large out of pre-trained models. So we've heard a lot about RAG, Retrieval Augmented Generative AI. So before we go there, back in February, what we're looking at is how can we provide a similar ChatGPT experience to our internal users using our own content corpus. And one of the first things that we tried is can we try fine-tuning the FLAN-UL2 models, the 20 billion parameter models. It was hallucinating a lot, and we finally ended up using RAG, and that worked out very well. This is still a proof of concept. It has not gone live yet. We hope to take this to production in a month or so. So what we figured out is that if you want to deal with security, right, we want to make sure that the generative AI, the response that LLM creates, it has to maintain the security, make sure that the user is only entitled to see what they have access to. Making sure that there is less amount of hallucination, and three, ability to provide citation to say where this answer was generated from. For those reasons, we use RAG approach. And again, just like talked about earlier, we are using a hybrid search methodology, which would get in information from BM25 results, get in the information from the semantic search results, and use a custom AI re-ranker, which also takes into a lot more information, including the popularity, the recency, historical queries, etc. We bring in all this information together as signals to the AI re-ranker module, which will then suggest which are the best chunks to use. Using those chunks, then we use LangChain, and we build algorithm on top of LangChain to figure out what are the best chunks to use, how to stuff it together, and then pass it ultimately to the LLM to generate the answer. And we did it on entire sales data that we had, as well as on Cisco.com. When we did demo to the sellers, it was a humongous positive feedback. Some of the use cases that we heard is an ability to do sales pitches. You can create a prompt like create a sales pitch, highlighting case studies for so areas. You can do product comparison. You have two products, and it'll automatically pick up information from different set of documents in the content corpus and create a tabular data view of doing a product comparison. You can create PowerPoint outlines. It can do creative content writing, etc. So the ability to have a ChatGPT-like experience using our own data is a huge productivity improvement for our sellers, and that's what we're aiming towards with this. And this is surprisingly accurate. It took a while to get the relevancy right, and as you heard earlier today, the key is to make sure that the chunks that you pass to the LLM is the most accurate one, because if the chunks that you pass is inaccurate, the LLM is not going to generate a good response. And this is an example of how that was working. Essentially, given a user query, it would generate embeddings out of it. It would figure out what are the best chunks, and then The prompt builder will create the right prompt to, to the LLM to use those chunks to ultimately generate the response. Now let me talk about the other use cases that we've been working on in the last 1 to 2 years. One is AI research assistant, where given a support ticket, we are trying to figure out what are the most similar support tickets, which is very similar to what the the one that the current engineer is working on. So again, we have fine-tuned this embeddings on this content corpus. And we are doing an KNN search with Elastic, with search on around 5 million support requests with KS 10,000. One of the interesting thing is the summary that you see below the title is also generated using a generative AI model. 2 years back, we used a bot model to create the summaries with support tickets to be very concise. The next use case is called Borg alerts ranking. So Borg alerts are alerts that are created for every support ticket case attachments. And the problem that we're trying to solve is, okay, given this case attachment alerts, how do I figure out, there are probably 100 to 500 of them, how do I figure out which of these alerts are most semantically similar to the content of the case? And essentially what we did is we created embeddings on each and every alert that used to get created. We had embeddings, different kind of embeddings created per support ticket. And ultimately, we're doing a quotient similarity match, a dot product match against the SR case embeddings, as well as all the alerts embeddings in an Elasticsearch search manner. So in real time, we used to generate the embeddings index into Elastic as and when these alerts gets created. So, in one of the optimizations that we've done is some cases the case nodes is large enough. We use key phrases extracted from the case nodes and then use those key phrases again to generate the embeddings, so that it fits in the 512 token context window. Now let me talk about how we build a scalable enterprise search platform in GCP. So on the right-hand side, you'll see a bunch of connectors. So what we have done is we have standardized on all of the connectors to be run as a data proc job, or in on-prem, we run jobs using a Spark operator in a custom Kubernetes cluster. And all of these connectors, whether it's a crawler, an API connector, all of these connectors essentially uploads the documents, crawl documents in GCS. And in fact, we have a crawler that is based on the Spark as well. We found it much more fast and lighter than Nutch. So we actually took an open source crawler and added enterprise crawler capabilities into it to run this as a Spark job. So what we do is the connectors would pull in the data from the sources, upload to GCS, and the crawled data along with its metadata is sent, the reference of the GCS URL is sent to PubSub, which again goes into a document processing pipeline. So we use Google's GCP data flow as a document processing engine. This is where we do things like text extraction, business logic transformations, etc. And the output document from the data flow, again, gets stored back as a process document in GCS, and the reference is sent to another PubSub topic, which is pulled in from a couple of AI pipelines which are running as microservices in GKE. And as I mentioned earlier, this is deployed in both as a global deployment, in both in US as well as in Asia. So we do the processing in one region, then the ultimate index is stored in 2 different regions. So the AI pipelines does the job of things like chunk extractions, generation of embeddings, neural question generation, etc. So, and ultimately, all of them gets indexed into Elastic via Logstash, which are running as, again, microservices in GKE in both the regions, in 2 Kubernetes clusters, in both in Asia as well as in US. So the Logstash alone has got custom Ruby plugins, which would pull in the documents from GCS, basically retrieve from PubSub, and then downloads the documents from GCS, and then gets sent to Elasticsearch. Again, Elasticsearch is run using the ECK operator, Elastic Cloud for Kubernetes, and again, deployed in 2 GKE clusters. We use Anthos service mesh to connect the clusters together. Initially, we were using Istio in a multi-cluster replicated control plane setup, and later on, we migrated everything to Anthos service mesh. Now, here is where the UI and all the AI microservices, all the AI inferencing services used to happen. Like before, we used to optimize the model using TensorRT and use NVIDIA Triton Inference Server to serve it in an optimized manner, because the speed matters a lot when you do a search. The AI layer has to be fast enough so that end-to-end user experience time is not impacted much. So we always used to optimize the models using TensorRT and deployed in NVIDIA. Now, with the newer models, we are now using Hugging Face TGA, text generation inference. So ultimately, there are 2 network endpoints created for the load balancer, and for the API, we use APG, and we use the Google's load balancer to front end out. For security, we use Cloud Armor, et cetera. Now, what you've seen is, overall, when you combine the speed and the accuracy of Elastic and the power of generative AI, you've seen that you can create amazing and delightful customer experiences. Thank you.